So Ohanian 5.93, let me just draw a picture first, has one block of mass M1 sitting on a frictionless table. We haven't officially discussed friction before getting to this problem. So it's sitting on a horizontal frictionless table attached over an ideal pulley with an ideal rope to another block M2 hanging vertically from that same string. So we're given, in principle, M1, M2, and G, assume we know the acceleration of gravity, and we're asked to find the acceleration of the system, and it'll be the same for both masses because they're in magnitude, because they're attached by an ideal string, and find the tension in the string. So it's obviously, I hope, a Newton's law problem, at least for now. And so we'll need Newton's law, which means we start with a free body diagram with definitions of our coordinate system, etc. So I need a free body diagram, one for each object or mass in the system. Okay, so let's start with M1. And I am going to use, there was a hint in the problem that you don't need to use the same coordinate system for each. And since when I get to M2, I intend to choose positive y down, x horizontal. What I want to do for M1 is to use the same coordinate, positive y to the right, so that an acceleration for M2 is equal to an acceleration for M1. I'll pick x in this direction, although x won't matter for this problem. Notice that if I had chosen the conventional xy coordinate systems for the masses, I'd have had an acceleration in the x direction for M1 and an acceleration in the y, or maybe the negative y direction for M2. Then I'd have to write out explicitly xy equals either plus or minus, or x1 equals plus or minus a2, and things would have been more complicated. So this choice of coordinate systems is a wise choice that makes my life simpler. You could solve the problem with other choices, but your life would be a little bit harder. The problem would be harder. So in any case, these are my coordinate systems for the two masses. Let's go ahead and draw the forces. There's a force of gravity pulling down on M1, and there's a normal force pushing up on M1. Now these aren't an action-reaction pair. They act on the same object. They both act on M1, and that's what we want, the forces on M1. On M2, we also, almost forgot, we also have a tension pulling to the right on M1. That's the string. The string pulls on both ends with the same tension because it's an ideal string. On M2, we have a force of gravity acting down and the string pulling up on it. The string pulls in at both ends. So those are my free body diagrams. Okay. What's the next step? The next step in the traditional Newton's laws problems is to apply Newton's law, the sums of the external forces. And notice these are all external forces acting on these masses. The sum of the external forces, let me just write that down. The sum of the external forces equals the mass times the acceleration. Now this would be a vector equation, so you would have the x and y components, but in our case, it's essentially a 1D problem. So we don't have to worry about vector components, again, because of the wise choice of the coordinate system. So let's start with the Newton's law applied to M1. We have the sums of the forces. This will be in the y direction on M1. I just look at my free body diagram and I say, there's T, and that's it. The sums of the forces in my y direction, there's only the tension. So that has to be equal to M1 times its acceleration. Well, that was simple, but now let's look at M2. For M2, the sums of the forces in its y direction on M2, and in this case, we have two forces in the y direction. We have, let me show you, we have M2G down, which is our positive direction with my choice of coordinate systems, and a T up, which is our negative direction. So I write that as M2G minus the tension, and the sums of those forces has to be equal to that mass, which is M2 times its acceleration. Okay, so now we've done much of the physics. We've examined the problem, set it up with the free body diagrams, decided what physics concept to use, which is Newton's second law. Now we put on our math hat and say, well, how do we solve for the acceleration and the tension? First, notice that there are two unknowns, and I've got two independent equations connecting them. So the first thing I do is, do I have enough information to solve for it? Two unknowns, two equations, so the answer is yes. The next thing is, what's the method that you want to choose to do this? There are a couple ways to think about this. For example, I could just add these two equations, then t minus t would be 0. I'd have an equation that says m2g equals m1 plus m2a, or you can just use t equals m1a and plug that into here. So let me just do this and just say I'm going to plug in t equals m1a into this equation. That leaves me with m2g minus m1a equals m2a. And there may be other ways to solve this, but whatever you choose is okay. Then all I need to do is, and what I've done is eliminate t from these equations so I can solve for a. I need to get a on the same side of this to do that. So let me write a times m2 plus m1, or m1 plus m2. Now that's moving this term to that side, but then I'm shifting it back to this because I want to. That's just algebra. And this will be equal to, again, m2g, which will be left on that side. And what I've got then is the acceleration equals m2 divided by m1 plus m2 times g. That's one of the things I was asked to solve for. Now I need to go after the tension, and I could do that in a variety of ways, but the easiest thing to do, I think, is just to use this first equation, which says the tension is equal to m1a. Well, I know a from up here, so that's just equal to m1 times m2 divided by m1 plus m2 times g, and that's my answer for the tension. So I've answered the problem, but I don't want to actually stop there. Let's think about this for a moment. Do my answers make sense? And the way to check that is probably to say, well, what happens to some special cases I think I understand? Well, if m2 is much, much greater than m1, then that means that basically this end of the rope is free and m2 should just be in free fall. So let's see what our equations give us. If m2 is much, much bigger than m1, okay, then the acceleration equals m2 divided by m1 plus m2g. If m2 is much bigger than m1, I just ignore this. I'm left with m2 divided by m2, which is just 1. Acceleration is g, just what I expected. It just falls. What's the tension in that case? Well, the tension is equal to, well, if m2 is much bigger than m1, let me write this out again, divided by m1 plus m2g. If m2 is much, much bigger than, I'm sorry, you can't see that. If m2 is much, much bigger than m1, then I ignore this. Once I've ignored this m2 cancels that. The tension is equal to m1g. Okay, and if m1 is very small, then this tension is going to be very small, which is what we expect. It's interesting to note, and this is something you might not have guessed, that if m2 is much, much bigger than m1, it's m1 that determines the tension, because it's still the only thing resisting the fall of m2. If m1 went to 0, then the tension would go to 0. And if you want, you can also check the situation for m2 much less than m1. And what would you expect to happen in that case? If m2 is small, then basically it's just hanging there, not because m1 is preventing it or at least slowing its acceleration down. If m2 is much, much less than m1, what we see from our equations, a is equal to m2 divided by m1 plus m2. G, m2 is small, so ignore that compared to m1. And then we have something small divided by something large, and so this does in fact go to 0, or at least it gets very small, a small fraction of g, just as we expected. The tension, which is equal to m1 m2 divided by m1 plus m2 g. What happens if m1 is much bigger? Then again we ignore this. Then the m1s cancel, they're left over, and you have, this goes to m2g, which is again what we would expect if m2 is just hanging there. Then the tension in the string would be about equal to the weight of the mass hanging from it. So everything seems to make sense, and I'm confident in my solutions.